No. The orbital. I'm sorry. The 220 exam was on Tuesday. I was looking on Thursday. I was like, where's the 220 exam? It's gonna be good here. Yes. I'm not doing anything. No. I already told. I'm only getting like cheap lunch and stuff.
This is you here. What's my name? What's my name?
What's your name?
Yeah.
What's your name? No, your name.
Oh, Manny.
Manning?
Yeah. You don't know my man. But I'm your favorite student.
Oh, okay. Is it Manning? Guzman. Okay, Guzman. Yeah, I'm not gonna give credit. Look quite different. Where's the goatee?
At least he doesn't have the long hair.
What's your name?
George.
Last name?
Uiuc.
Okay, yeah, I see you. Look quite different too.
It's the same the head on,
You're learning your name.
Shopping.
yes.
And you? P-E-N-G? P-E-N-G. What kind of find yours? Elliot
is the last name.
Alex?
Yeah,
Oh yeah, I see you.
Yeah, what's he look like? Let me see. Yeah, look at that cheesy smile.
Some of the other material.
Okay, let's get started.
I'm your favorite student, though, right? Just ask.
Let's get started. Any questions before we move on? Okay, let's get moving. It's really cold out there, so I appreciate you coming in despite the cold weather. So we'll talk about differentiators and integrators, or differentiating circuits and integrating circuits. Okay. So things that differentiate signals for you. This will be signals that are a function of time. Like I might be a function of time, and then V might be a function of time. There will be circuits that will find the IT dt for you. And then some of them will find the VT dt for you. These are called differentiators, and we will also design circuits that will do integration for you later on. But let's start with the differentiator circuit. Okay, differentiator circuits. And we already saw some devices that have differentiation relationship. Those are your capacitors and inductors. And those come from the VI relations that we have for these devices. And for the VI relationship, we have I in C dV dt. Oh. Some device, and then we have V is to the L dI dt. So what is the first device that has this differentiation relationship? Anybody? Capacitor, right? It's a giveaway, right? And then the second one is the inductor. The C and the L giveaways. Okay. So this naturally differentiates the voltage for the capacitor. This naturally differentiates the current for the inductor. And just have an example, say 3.6 from the textbook. Then say if we have a voltage source that is sinusoidal, that is 5 cosine of 100 t, and this is in terms of volts, say. Okay, a signal that looks something like this, and this is called an AC signal, a sinusoidal signal, or time harmonic signal. So they're given different kinds of names. Sometimes they're called time harmonic, sinusoidal, AC. AC stands for alternating current signals. And if it were to be used to pass through a capacitor in this manner, say if we have a capacitor that hook up to a inductor, we ask ourselves what the I of t should be, then we will just use this equation to find what the I of t is, and I of t is just equal to C dV dt. And if you were to differentiate this with respect to time, when you differentiate the cosine, what do you get? The minus sign, right? But if you differentiate the cosine of 100t, what do you get? Minus 100 sine of t. So you get minus 100 times 5, you get minus 500 sine of 100t. Okay, in general, if V of t is equal to V naught cosine of omega t, omega is used to represent the frequency, dV dt is equal to omega V naught times omega sine of omega of t. Okay. And then I of t is just equal to minus C V naught. I should multiply by a C here as well. Okay, I should multiply by C here as well. C V naught omega sine of omega t. Okay, so that is the general procedure to find the current in this circuit when the capacitor is hooked onto the AC source, or the capacitor is hooked onto an AC source. Okay, so a very simple differentiator circuit. And then if you have example 3.5 of the textbook, let's erase this one. So everybody has copied this one, right? So I can erase this. So in this case, we have the current source going through an inductor, and that the current source has a current IT, and I ask myself what V of t should be. Then you go to this circuit over here. The inductor might have the value of C and L, and the capacitor has the value of C. So you just write down that equation and say that V of t must be equal to L di dt. Okay? Now let's do some I that is somewhat fancy looking. I of t looks something like this, that I of t is 0 in the beginning of time, or until time is equal to 0, then it goes up linearly as a straight line. Okay? I of t is equal to 0 for t less than 0, is equal to t for t larger than or equal to 0. You understand this kind of notation, right? Does everybody understand this notation? So it's easily understood. So that describes that signal over there. And if you differentiate to find out what v of t is, it will be just a differentiate of this. And if you differentiate 0, you get 0 for t less than 0. If you differentiate t, you get 1 for t larger than 0. So the signal here, v of t, will be 0 in the beginning of time, initially. Okay? At this juncture, when it switches over to be a straight line, when it differentiates, it becomes 1, but multiplied by the value of L. Okay, so v of t will look something like this. And L is given in the textbook to be something like 1 Henry. Okay, inductors are measured in terms of 1 Henry. And you get v of t to look something like this. Things that change with time, signals that change with time, are called transient signals. Okay, this can be thought of as a time-varying signal, a time-varying signal. This could also be thought of as a time-varying signal if you want. Those are called transient signals. Are there any questions so far? Okay. Everything is quite simple as of this moment. Let's see what the story is when we hook this thing up together with an op-amp. And you have learned about op-amp. So let's look at the case of an op-amp differentiator. Okay. So let's design an op-amp that looks something like this. With a minus here, a plus here, and then have a resistor that hooks the feedback resistor. And let's assume that all the signals are transient, so that they're functions of time, and that V plus is grounded, V minus is hooked this way. So we have Vs of t, that is some transient signal. Okay, we ground it in this manner. And ask ourselves how the output voltage look like if V of S of t is not a constant but some signal that changes with time. Okay. In this thing, we know that V plus must be equal to 0, and V minus is approximately equal to V plus, which is equal to 0. So V minus is almost grounded as well. Okay, V minus is almost grounded. So the voltage drop across the capacitor is just Vs. Okay, the voltage drop that appears across the capacitor is just Vs. Okay, and if I were to write the IV relationship for this capacitor, I will have IC, the current that goes into the capacitor, must be equal to C dVs dt. Okay, so that is the first equation I get. The capacitance current is given by this thing because V minus is approximately equal to 0. Okay, but there is another way of finding IC. If I were to look at this IF, the feedback current that flows in that direction, or it could be, IF. What do you think the relationship between IF and IC would be? They're very close to each other, right? Because nothing goes into op-amps. Op-amps are high input devices. almost no current can go into them. So this current will veer its way up and become IF. Okay? So hence this current IC is also equal to this voltage minus this voltage divided by the resistor R. Okay? So this voltage is 0, so it's 0 minus V out time divided by R. Because this is also IF, which is just equal to IC approximately. To a very good approximation, IF and IC are equal to each other. So from this equation, we immediately deduce that Vs and Vout are related to each other. So I can write the fact that Vout as a function of time is just equal to minus RC dVs, which is a function of time dt. So this is a op-amp differentiator circuit. The output is related to the derivative or the time derivative of the input signal Vs. Okay, any questions regarding this very simple capacitor differentiator circuit? We can also make differentiator circuits out of an inductor. Okay, let's see how we can do that. In that case, you have an op-amp just like what you had before. Okay? And then you hook an inductor in this manner. And then we have V out of T, and this is an L with the voltage drop across it, say, and then the current I that goes in that way, the source resistor that we call R, and then we have the source voltage V of T, and this is grounded, this is also grounded. Okay, let's write down the relationship between the output voltage and the input voltage V sub S over here. Okay, first I would like to say that V plus, what is the value of V plus? 0. And the value of V minus is also approximately equal to 0. So we have V minus being approximately equal to V plus being equal to 0. So this point is almost grounded. So I can write down the current I that goes through that resistor R quite easily. So I can say that I must be equal to V S over R. Okay? And then that I that flows here must also be very close to the I that goes through the inductor. Okay? But I know that V for the inductor, VL, must be L VIL dt. Okay, VL must be equal to L VI dt. And this is the voltage drop in this manner. Okay, VL is that voltage drop in that direction. And then I have this relationship over here. And then this must be equal to, according to this equation, IL and I are the same, so it's L dVs dt divided by R. Okay, I just take the R out, substitute this into here, and put the Vs. Vs is the only thing that changes with time. So initially I have something like d dt of Vs over R. And then I take the R and put it outside, because R is a constant. So I have L over R. Okay? But VL and VO, how are they related? How is VL and VO related? If I say that this is VL, how is that related to VO? VL and VO are the same, different, completely different, just the opposite of each other. Multiple choice question. What is VO and VL? How are they related?
They're opposites.
They're opposite to each other, right? VL is the voltage drop in this direction. This is almost 0 volt. So VO is just the voltage in that direction. So this must be equal to minus VO. VL and VO are just related to each other by a negative sign. So finally, I have the fact that VO must be minus L over R dVs dt. This is the differentiator relationship for this inductor circuit. Okay, are there any questions so far regarding differentiator circuits?
Explain the relation between VL and VO again. Why is like opposite?
The relationship between
VL and VO.
VL and VF.
V output.
This one?
Yeah.
Okay, VL is the voltage drop. When you write down this IV relationship for an inductor, it looks something like this. If I put it upside, right side up, maybe it's easier for you to see it. Okay, if I were to write the VI relationship for this inductor, VL is L VIL dt. So the voltage drop is from here to here. VO is the voltage at this point, measured with respect to the ground. Okay, this is the voltage with respect to the ground. So this is the voltage above ground. So if I look at this circuit, this point here is VO above ground. This point is almost grounded. This point is grounded. This point is almost 0. So VO is a voltage drop in this direction. VL is a voltage drop in that direction. So they are opposite of each other. Okay, so I put VL to be minus VO. Okay, so this might be hard to stomach in the beginning, right? Why am I putting all this minus sign all over the place? When am I swinging my arm here and swinging my arm there? But you have to think a little bit. And they are actually opposite of each other. Right? So you have to learn how to put negative signs here and there. Negative signs do not come naturally to human beings. They were not invented until very recently. The concept of 0 was not invented until quite recently. In the beginning, when we were primitive men, we didn't have the concept of a negative sign. I believe the concept of 0 was invented in India quite a few thousand years ago. Okay, before that, people never used the concept of zeros. Okay, neither do we use the concept of negative signs. So you have to think a little bit as to what negative signs mean. It is not natural. Okay. Even worse is imaginary numbers. Okay, you will have some of those in your test. Square root of minus 1, what does that mean? Okay, if most of you do not have problem with this, let's look at other things. Let's look at integrated circuits now. We have looked at differentiation. So let's start a new topic and call this integrated circuit. So you still do that with capacitors and inductors, but you do it in a different way. So that you flip the equations around so that you can have an integration somewhere. Okay? Let's look at I, T, which is C dV dt for the capacitor. But if you turn this equation around and integrate this, if we integrate this equation, we get something like this that says that if I were to integrate this equation from A to B, IT dt, okay, I will get the integration on the right-hand side, which is just V of t, evaluated at t equal to A, t equal to B, okay, which is equal to C BB minus VA. So I turn this equation around and make the relationship between voltage and current to be an integration. Okay? So in general, for a capacitor, I can write as such that VB is equal to VA plus 1 over C integration of A to B IT dt. Okay, so this is a general relationship. But if you want to write these variables in terms of time, okay, then I can say that V time at T equals to B must be V0 T 0, okay, plus 1 over C T0 to T, and then I can change the time variable to tau. Since this is just a dummy variable, I can rewrite this equation in this manner. So that it's valid for all T. Let me see what notation the book used so that I use the same exact notation here as is used in the textbook. Okay, the textbook just called this VT0. Okay, the voltage at T0. If you look at this equation is valid for all time, T. If I set T to T0, what would happen to that integral? If I set T equal T0. T0 is the beginning of time. You can think of T0 as beginning of time. If you look at the time axis, T0 is the beginning of time, and T will be another time on the t-axis. If I set t equal to t0, what will happen to this integral? 0. So this is the value of the voltage. If I were to plot this as a function of time, okay, this will be the value of the voltage at t equal to t0. So this is Vt0, and this is just Vt. And you can write a relationship between Vt and the capacitor and the current in the capacitor in this manner, in an integrative fashion. So if you were to look at the current that goes into the capacitor, if you imagine a current that looks something like this, that the current looks something like this. Okay, a current that looks something like this that goes into the capacitor. You ask yourself what the voltage is through the capacitor. Then you find the voltage through the capacitor by just using this relationship. The V of t is just the integration of the current according to that relationship. Okay, there's no current. When t is less than t0, we can assume that t0 is equal to 0 here. So this is the beginning of time. So there's no activity when t is less than t0, since there's no current there. And let's assume that Vt is equal to, let me see, Vt is equal to some constant. Vt is equal to some constant voltage before that. So before this other term, the second term sets in. If t is less than t0, this term doesn't contribute. And it will just have Vt0 being a constant. Okay? And then as I make t larger than t0, the second term will pick up. The second term will pick up, and I need to compute the integral of this. And if I were to compute the integral of this in the beginning of the time, I will have some positive contribution. Okay? I will get more and more as I integrate more, find the area under this curve. So eventually, I get the diminishing return from my integral. I get a lot of return in the beginning, and finally I get less and less accumulation of the integral. So eventually when I go out here, there's nothing changed if I say integrate up to this point compared to integration up to that point. So the curve will look something like this. Okay? And this is how v of t look like if we were to perform the integral. And you can substitute some functions in here too as well if you want to. You might substitute this as I0 times e to the minus alpha t, and that fits this curve, and then you integrate mathematically, and then you can get this curve, and you find that the curve actually does look like that. But I'm not going to do that. Those are some details that you might want to do at home. Okay, but I just heuristically tell you that when you integrate this curve, you get the curve. Okay? Okay, let's do another example, okay? Example 3.7. But before we do that, let's go through something that is quite interesting, that capacitor voltage can't jump. Okay? Capacitor voltage cannot jump. If you have a voltage across a capacitor, it cannot jump. That's what we see here. We can see that the current through a capacitor can jump, but not the voltage. What is the reason for that? It's because the current, as a function of time, is the capacitor times the derivative as a function of time. If there's a jump, say if v of t looks something like this. This is not possible. That's what it means. Capacitor voltage cannot jump. Are you familiar with the concept of a step function? All of you know what a step function is, right? And are you familiar with the concept of a delta function? All of you know that, right? EC 110 taught you that. So, no? No, not a delta function?
Didn't learn anything.
You didn't learn anything in EC 110?
Just pointless.
So, if you have a step function, okay, if I have, say, a voltage signal that looks something like this, if I differentiate this, what do I get? I get the delta function back. Maybe it's too difficult to conceive what a step function is. Let me draw this as a precursor to a step function. This is a precursor to a step function. A function that looks something like this. It has a ramp. It does not abruptly rise from one value to another. If you were to differentiate this function, what do I get? I get 0 here, right? And then at this ramp, I just get a constant value, right? And then beyond that ramp, I get back 0. Okay? So derivative of a ramp function is a pulse. Okay? What happens if I make the ramp sharper and sharper? If I make the slope steeper and steeper? The pulse gets to be taller and taller. That is called a pulse function, an impulse response. And something that you will learn and use again and again in electrical engineering. Okay? So if it is the step function instead, what you should have here is an infinitely tall pulse. Okay? The picture of that going to infinity. This is called an impulse. And that is something that actually has a height that is infinitely large. Okay? So if I have a jump discontinuity in my voltage, if I differentiate it, I must get something that maybe finite here and then suddenly shoot up to infinity, and maybe something finite here. Agree if you differentiate this function. So, but nothing is infinite on the left-hand side. Nothing is infinite. So this is not possible. The fact that the voltage has a step discontinuity is not possible because otherwise you will produce a function that is infinitely poor. And there's nothing else to balance it. There's no current that can balance this function if I just look at this ideal relationship. So a jump discontinuity in the voltage is not possible across a capacitor. Okay? I hope you get this. So let's do another example. Let me see. Maybe I do the op-amp examples first. Make sure that I cover those before I cover other examples. I think the op-amp examples are the most difficult. Let me cover those first. Okay. So you know what these are. They just differentiate things. And let's look at the op-amp integrator. Okay, because we saw an op-amp differentiator just now. And then we switch over to integrator circuits. And you just revert this kind of things the other way around. You can also do that for the inductor as well. You can reverse this circuit around, make it into an integrator circuit. Okay, we did that for the capacitor. And then now, I'd like to show you the case of what happens when you connect this to an op-amp and convert an op-amp into an integrator circuit. And the op-amp integrator looks something like this.